As we start our unit on exponents, exponential, log, and power functions, it's really important that everybody really be confident about your exponent rules. So I want to review exponent rules. In class we did this as a group, so if you are just listening to this video, it might be a good idea to see if you can pause the video and do the first 5 problems. See what you would get if you simplified the exponents here and distributed here. What would you get? And then unpause and see if you're correct. On the first one, you should have gotten a to the 5th, and the second one a to the 6th. Now lots of times students will be confused about their exponent rules or try to memorize rules but not really understand which one is which and when do you use it. Often students might have made a mistake and called this a to the 6th, or they might have made this and said a to the 2 to the 3, a to the 2 raised to the 3rd power to make it a to the 8th. Or maybe a to the 5th. So how do you know that this is a to the 5th and this is a to the 6th? So what you need to do is remember that when you raise a number to a power, or any quantity to a power, that you are multiplying that quantity times itself that many times. So this is just a times a, and then a times a times a, which is a to the 5th. And so when we have two numbers with the same base, we can just add their exponents. So this is a to the 2 plus 3 power. And that's where you get a to the 5th. Now when we see a squared to the 3rd, we are multiplying the quantity a squared times itself 3 times. So we're saying a squared times a squared times a squared, which means we're adding 2 plus 2 plus 2, or 3 times 2, which is 6. So this is a to the 2 times 3 power. So you multiply the exponents when you raise a power to a power because you're just multiplying that whole quantity times itself. So if you forget your exponent rules, just do a simple example like this to help you remember when to do what. Now distributing tends to throw students off. The correct answer for the first one should be 2a plus 2 plus 2b, because multiplication distributes over addition. Because this is just saying a plus b plus another a plus b. So I have a total of 2a, a plus b plus another a plus b, which means I have a plus a, which is 2a, and b plus b, which is 2a. A plus a times b squared should end up being a squared times b squared, because in this case you're saying a times b times another a times b. And just like with addition, addition is commutative. In other words, you can switch the order of it and you're still adding in the same way. Multiplication is also commutative. I could switch the order. I can say a times b times b, and it's the same quantity, and that would give me a squared times b squared. So that means that exponents distribute over multiplication. But many students mistakenly think that a plus b squared is a squared plus b squared, but this is not correct. This is a big no, okay? It is not a squared plus b squared. The correct answer is that a plus b is equal to a plus b times a plus b. And when you multiply that out, you get a squared plus ab plus ba plus b squared, because you have 4 different multiplications going on. A times a times b, b times a, b times b. And this simplifies to a squared plus 2ab plus b squared. So when you distribute, you need to remember the hierarchy of operations. On the our lowest operation is addition and subtraction. Then the next hierarchy up is multiplication and division. Then the next hierarchy up are powers. So when we each operation distributes over the next lower operation. So we can say that multiplication distributes over addition using example 1. So here's example 1. Here's this rule. Exponents distribute over multiplication because exponents are the operation that is one step higher than multiplication. It also distributes over division as well. So this is number 2. But exponents do not distribute over addition because exponents are not one tier higher in operations than addition. Exponents don't tell us repeated addition, they tell us repeated multiplication. So we cannot do that last distribution. And that's where a lot of students go wrong with using exponents. That is a very common mistake, this mistake that we saw in example 3. Now, once again, pause the video for a second and look at these 3 expressions and say whether you think they're true or false. And I really encourage you to do it yourself first before you listen because it's helpful to think about that. So pause the video, mark them true or false, then turn the video back on. Number 1 should have been marked false. We have 2 expressions raised to a power that have the same base. So that means we're going to add their exponents. When we add the exponents, e to the x plus x is equal to e to the 2x power, not x squared. We're not multiplying x times x. It's not 2e to the x. That would be e to the x plus e to the x would be 2e to the x. It's e to the 2x power. The second one is also false. Many students think because they see a set of parentheses that they need to distribute. But we learned up here that multiplication distributes over addition. Multiplication does not distribute over multiplication. When we see 2 times the quantity xy, that's just 2 times x times y, which is 2xy. So that's what this should be, is 2xy. The third one is the trickiest of the 3, but it is also false. And the reasons it's false is because we have this exponent here. If the exponent were not here, then we could say 2a plus 2b. But because the exponent is here, we have to start with the highest ranking operation first, which is exponents, and apply that first. So the first thing we have to do is think about this is 2 times the quantity a plus b times the quantity a plus b. So we have 3 things multiplied together. 2 times a plus b times another a plus b. If it was 2 times x, that would be 2x squared. It would not be 4x squared. So I cannot distribute the 2 to both of these because these 3 quantities are all multiplied together, just like in example 2. 2 times x times y. 2 times a plus b times a plus b. So I could distribute the 2 over the first quantity, but not the second one, and I could have 2a plus 2b times a plus b, or, because I can multiply in any order that I want, I could do the squared part first and then multiply everything by 2. Or I could say 2 times the quantity a squared plus 2ab plus b squared in parentheses, and then multiply everything by 2, because then I would be distributing over addition. So I had 2a squared plus 4ab plus 2b squared. So either way I did it, I would end up with 2a squared plus 4ab plus 2b squared. If we multiplied this out, we'd end up with 4a squared and 8ab in the middle. Okay, so the 2 only distributes over one of the a plus b's, but not the other. Once again, this is a very common mistake that students make, so be careful of this one. All right, let's go to the second column. In the second column, we're dealing with negative exponents. So most people have learned that a to the negative first is 1 over a. And that is a correct statement. But what I want you to think about this is that a to the negative first is equal to 1 over a, the reciprocal of a, to the positive 1. So this is the reciprocal of the base. So the base was a, and the reciprocal of the base is 1 over a. And when we use the reciprocal of the base, then we make this positive. So if I apply this same rule to what I just did, a to the first times a to the negative first is a times 1 over a, which is when we multiply a number times its reciprocal, we get 1. We could also apply the exponent rule that we learned over here, that when you multiply two numbers with the same base, you add the exponent. So we can say a to the 1 plus negative 1, which is a to the 0, which is also the same thing, so it has to be 1. So this is an explanation of why a to the 0 equals 1. Now, when we have two of the same base raised to powers but divided, what do we do? So think about that the numerator just is a times itself 4 times, and the denominator is a times itself 2 times. So we divide a by a and we get 1. We divide a by a again and we get 1. So we just end up with a squared. So what exactly am I doing with the exponents? Let's come back. I'll come back to that in just a second. Now we know here a to the 4th over a to the 4th, well, we have the same thing in the numerator and denominator, so this is just 1. Now if we apply the same thing we did in the first of these 3 examples to the third one, we would have a times a over a times a times a times a. A divided by a is 1. A divided by a is 1, so this gives me 1 over a squared. Now, you might be wondering, what exactly did we do with the exponents in this first one? Did we subtract them or did we divide them? Well, clearly here, we didn't divide them because that would be a to the 1/2 power. So we must have subtracted them here. So that turns out to be the case. Just like when you multiply two numbers with the same base, you add their exponents. When you divide two numbers with the same base, you subtract the exponents. 4 minus 2 is a squared. This makes sense on the second example because a to the 4 minus 4 is a to the 0, which we know already is 1. And then the third example, we can think of this as a to the 2 minus 4, which is a to the negative 2, which we've learned is 1 over a squared. And if we do 1 over a times 1 over a, we get 1 over a squared. Now, you don't always have to write it in those 3 steps. I can go from a to the negative 2 directly to 1 over a squared, but I want you to know that you are multiplying the reciprocal by, or you're raising the reciprocal to a positive 2 power here. And the reason I want to emphasize that is because when we get to an example like a over b to the negative 2, it's very helpful to remember I just need to take the reciprocal of the base and make this b over a to the positive 2. That's a lot easier than doing 1 over a fraction. Okay, just remember this is the reciprocal. Then this is the same as b over a times b over a, which is b squared over a squared. So just like exponents distribute over multiplication, they also distribute over division. So I can just apply the exponent to the numerator and the denominator separately. The next example, 2a to the negative 3rd over 3 to the negative 2nd. What if we have a fraction that already has negative exponents on individual components in the numerator and the denominator? Well, we can remember that anything raised to a negative exponent, if it's in the numerator, its reciprocal will end up with that term in the denominator. Or if it's in the denominator, its reciprocal will end up with that term in the numerator. So a to the negative third can become a to the positive third if I move it to the denominator, and 3 to the negative second become 3 to the positive second if I move it to the numerator. Now be careful. This does not say 2a, the quantity, in parentheses to the negative 3. A is raised to the negative third power, but 2 is just raised to the positive 1 power. So it does not move. It stays in the numerator. So this is 2. I'm going to move the 3 up to the numerator and make it 3 squared. I'm going to move the a down to the denominator and make it a to the positive 3. So this is 1 over a to the third, which means a is going to end up in the denominator. And this is, instead of 3 to the negative 2, it's like 1/3 to the positive 2. If I made this or the reciprocal, I could also, and I'm kind of doing this over to the side, you could also think this as 2 times 1 over a cubed times 1 over 3 squared. But realize how much more difficult that is to work with. When I divide by a fraction, I'm multiplying by its reciprocal. And so it's much easier just to take individual terms and just say their reciprocal means they move from the numerator to the denominator. So now 2 times 3 cubed is 2 times 9, which is 18. So it's 18 over a cubed. Now this next one incorporates a couple of different things. First of all, we have positive and negative powers. My suggestion here, though, is since I have both of these things in parentheses raised to a power, that I first distribute the powers, because everything in here is multiplied inside the parentheses. So that means I can distribute the power to everything in here. So I can have 3 squared, x to the negative 1 squared, y squared squared, and 6 to the negative 1 and x to the negative 1. So I'm going to distribute everything in the numerator and the denominator. So I have 3 squared times x to the negative 1 times 2 times y to the 2 times 2 over 6 to the negative 1 times x to the negative 1. Now, I just wrote this extra step so you would remember that when you raise a power to a power, you're multiplying their exponents, because this would be the same as saying 3x to the negative 1y squared times 3x to the negative 1y squared. So everything is being multiplied times itself twice. So this becomes 9x to the negative 2 y to the 4th over 6 to the negative 1 x to the negative 1. So anything that has a negative exponent on it, we can take the reciprocal. In other words, we move anything from the denominator with a negative exponent to the numerator, anything in the numerator from with a negative exponent to the denominator. So that would give me 9 times 6 times x times y squared all over x squared. Now, 9 times 6 is 54. And I also have an x to the first in the numerator and an x squared in the denominator. So x squared is x times x. So one of those x's is going to cancel out. So this would just become 1, and this would just become x to the first. And now I have 54 y to the 4th over x as my final answer. Now I took the time to do every step really deliberately and carefully differently so you could see all my steps. You could probably go from this step directly to this just by remembering how to multiply the exponents. Excuse me. So there is our exponent review.